Hello, welcome to lecture number 24. In the previous lecture, we derived the short wavelength limit. Now we'll do the long wavelength limit of the dispersion relation that we had derived. We saw that the omega squared is equal. The relationship between omega and wave number is called the dispersion relation, and omega squared is equal to f squared plus gh root k gh times k squared plus ky squared. And these waves are called these traveling waves are called Poincare waves, and these can travel in any direction. So now in the previous lecture we had done the short wavelength limit. Now let's do the long wavelength limit. So the long wavelength limit is equivalent to the limit omega is approximately equal to the Coriolis parameter. Okay. So we look at wavelengths much longer now than the Rossby radius of deformation. So long and short are with respect to some reference parameter. Hence, in this case, the Rossby radius of deformation is the reference parameter. So we have waves larger than the Rossby radius of deformation. Okay, so in this case, k squared is much less than f squared by gh. So plugging this into the dispersion relation, this yields us omega is approximately equal to f. Just plug in there in this dispersion relation, k squared is much less than f squared by gh. Again, dividing the whole system by gh and multiplying by the whole system under the root as gh and multiplying by root gh. So this is the case where rotation dominates. So these are both equivalent cases. So this is the case where the rotation dominates, and these waves are called near inertial waves. So these are called near inertial waves, and we have discussed this previously. The motion of these waves are circular. So inertial waves have circular motion, and this is what we have done previously during understanding the rotating frame of reference only. Hence, we have seen that the Poincare waves have frequencies higher than or equal to f, and hence they are always super inertial. That means it is higher than the inertial frequency. The time periods are higher than their frequencies are higher than the inertial frequency, and hence they are super inertial. And given that they have a whole range of spectrum, they fill up the or they fill up the spectrum between gravity waves and inertial oscillations. They are called inertia gravity waves. As we saw, there are two limits, two extreme limits. One where it does not feel the effect of rotation, where the phase speed is equal to the shallow water gravity wave speed, and the other one is where this frequency is exactly equal to the inertial, or near about equal to the Coriolis parameter, the Coriolis frequency. So these are they have a whole range of spectrum. They fill up the whole spectrum between gravity waves and inertial waves, and hence they are called inertia gravity waves. And because of the fact that the phase speed depends on the wave number, the phase speed depends on the wave number, except in the shallow water limit or the omega equal to f limit. These waves are called dispersive waves. These waves are called dispersive waves, and the relationship between the frequency and wave number is given by the dispersion relation. So dispersion, we can draw a simple schematic showing the relationship between the wave number times the Rossby radius of deformation and the frequency by the Coriolis frequency to be so this is the dispersion relation graph, and the waves in these lobes. So I'm shading these lobes, shading the area covered by these parabola. So these are Poincare waves, and these are Kelvin waves. So these values are +1 and -1. Okay. So this is a dispersion relation. So this is assuming f to be constant. So there's a reason why we are saying this f is a f constant, because we'll see what happens when f is varying. This is a graph that you can draw for the frequency and the wave number. Now we will see what happens when f is not a constant. Okay. There is a reason why we had to specifically mention the f being a constant. The assumption that the f is a constant. Now we'll see what happens if we don't have that. So we'll start with something called Rossby waves. So these are large scale planetary waves. These are also called planetary waves, and we'll see their properties. We'll derive the dispersion relation, and we'll see why they exist. And this comment about constant f has an important role to play. So we'll visit the Coriolis parameter again. We'll remind ourselves what we had done. So on a spherical planet like Earth, we said that f is equal to 2 omega sine latitude. Omega is the angular velocity, phi is the latitude, and this is how we define the Coriolis parameter. And since, till now we have been assuming f to be constant. That's what we've been doing till now. However, if we think about some systems which have very large length scales, for example, there is a hurricane which has, or a cyclone, these are essentially same things with circular motion. Let's say there is something on Earth which is very big, something like this. Now we can see that in this case the latitude of this portion is different than latitude of the extreme end. Two extreme ends are at very different latitudes. So one is at, let's say, phi 1, the other one is at phi 2. Now the Coriolis or the rotational effect that this feature is feeling is f1 equal to 2 omega sine phi 1 at one end, and f2 equal to 2 omega sine phi 2 at the other end. Similarly, if you have a current on the surface of the Earth, let's say this is the planet Earth, and you have a current which is flowing something like this, meandering current, multiple thousands, few thousands of kilometers. Again, similarly, this one end will feel a different f and the other end will feel a different f. Now it begets the question, what happens if this kind of differential f is being felt by the system? This is where we are going to question our assumption that f being a constant maybe will need some change. There's a simple technique to do that. So let's say there is a system which is f, which is like this, and at this center of the system, let's say the f naught is the value, the Coriolis parameter at a certain latitude phi naught. Okay, so this is the value of value f naught at phi naught. So this is a schematic of a current spanning multiple latitudes, let's say. And this routinely happens. If you see some videos of atmospheric or oceanic features, you will see that these are hundreds of kilometers and even 1,000 kilometers. And let's say this is the y direction. This is the direction along latitude, and our latitudes are organized in this way. So let RE be the radius of Earth. Now y by RE is a small quantity. Y by RE is a small quantity. In this case, the parameter f f can be expanded as 2 omega sine phi naught plus 2 omega y by re cos phi naught plus higher order terms. Now we ignore the higher order terms and we can write f equal to f naught plus beta naught y, where beta naught is equal to 2 omega by re times cos phi naught, and this is called the beta parameter. Now if you see, we are not assuming f to be a constant anymore. We have a formulation which takes into account the variation of f, the variation of the Coriolis parameter with change in latitude, and change in latitude from a certain reference latitude is given by this quantity y. And this formulation, where we have a variation where we include the variation of f with latitude for large scale planetary systems, large scale atmospheric and oceanic events, is called the beta plane approximation. If we do not take into account the variation of f with latitude, and that is what we have been doing till now in this whole course, that system, that assumption or that formulation is called an f plane approximation. So f plane approximation is what we have been dealing with till now, that is constant f, but in beta plane we include the effect of the variation of the Coriolis parameter with distance from a certain reference latitude, and that is called the beta plane approximation. And the parameter, the small parameter that gives rise to, that gives or that includes the effect of this change in f is the beta parameter. This is the parameter beta naught. It's called the beta parameter. Re is the radius of Earth and omega is the rotation rate. Now the governing equations, given that we include the effect of variation of f with latitude, the governing equations are del u del t minus f naught plus beta naught y times v equal to minus g del eta del x del v del t plus f naught plus beta naught y times u equal to minus g del eta del y, then del eta del t plus h del u del x plus del v del y is equal to 0. So these are the governing equations. Now as you can see, f is not being taken as a constant, and we have included the variation of f with latitude. This is of course for systems which are spanning multiple latitudes, that is, it is at least a few hundred kilometers away, 100 kilometers big in length scale, because each latitude, I mean, if it has to span multiple latitudes, it has to be a few hundred kilometers. Now this, we see that this system has a mixture of both large and small terms. Now we'll discuss this, what this means. The above set of equations have large terms of larger values and smaller values. Which are the smaller and the larger terms? So f naught is the fixed Coriolis parameter, g and h are large values, and the smaller values in the governing equations are the time derivatives and the Coriolis parameter that we assume to be small. Now the time derivatives are assumed to be small, and Coriolis, this beta parameter, sorry, this is not the Coriolis parameter, this is the beta parameter, it's taken to be small. The fact that we take this time derivative to be small, this means we are looking at systems which are changing very slowly. So these are low frequency waves. So we are concentrating our analysis on low frequency systems or waves. Okay, so we have larger terms and smaller terms. Smaller and larger are relative to each other in this set of equations. Now in the first approximation, assuming that there is the leading order balance can between the large scale between the large terms in the equations give us, so in the first approximation, that is the leading order balance, u minus u is approximately equal to minus g by f naught del eta del y, and v is approximately equal to g by f naught del eta del x. So we are throwing away the time derivatives and the term that has beta naught. So using these terms in the full equation, so we can again reiterate what we have been doing. So we are saying that this equation has a combination of large and small terms, and then we say that in the first approximation, that is, there is a balance between only the large terms, u has an approximate value of this minus g by f naught del eta del y. Similarly, v has an approximate value of g by f naught del eta del x. Now assuming that this is the leading order balance, this is the approximate value of the term, the velocities with some small corrections, we put them in the full equation, then we get minus g by f naught del square eta del y del t minus f naught v minus beta naught g by f naught del eta del x times y equal to minus g del eta del x. We are putting our approximate values of the velocities in the governing equation. So solutions to these equations, I'm writing in the next page. The solutions to the above equation gives us u equal to minus g by f naught the del y minus g by f naught squared del squared eta del x del t plus beta naught g by f naught squared del eta del y times y. Similarly, v g by f naught del eta del x minus g by f naught squared del square eta del y del t minus beta naught g f naught squared del eta del x times y. Now we have two kinds of terms here, one that is important for us to distinguish. The first balance, the first part, the first terms that you see are nothing but the geostrophic velocities. And these are the leading, these are the bigger terms, and these are approximately equal to u and v. However, this is not the full story. We have few terms which appear along with the which appear as corrections to the geostrophic velocity to the total velocity field. These terms or these components are ageostrophic components. These are the terms that arise due to the lack of balance between the Coriolis and the pressure gradient. So these are the ageostrophic components. Both of these add up together to create the velocity field. So we have the geostrophic component, we have the ageostrophic component. Both of these add up. Now substituting both of these velocities in the continuity equation, we get del eta del t minus rd squared. Rd is the Rossby radius of deformation, del t the Laplacian of the sea surface displacement, beta naught is the beta parameter, rd squared del eta by del x equal to 0. Rd is the Rossby radius of deformation. Assuming periodic solutions, again the coefficients are constants, hence we can look for periodic solutions of the type eta equal to eta naught cos kxx minus kyy minus or plus minus omega t. We get omega is equal to minus beta naught rd squared kx by 1 plus rd squared kx squared plus ky squared. So if you recall what is this relationship between frequency and wave number is called, and this is to remind you, this is called the dispersion relation, and this is dispersion relation for planetary waves. And planetary waves are also called Rossby waves. So this is the dispersion relation for Rossby waves. We can see from this dispersion relation that if if beta naught, the beta parameter, we're taken to be 0, that is we were assuming an f-plane, we were implementing an f-plane approximation, that is, we are not taking into account the variation of f with latitude, then we can see that we get omega to be equal to 0, which is the steady geostrophic flow that we said in the last class. It's a frozen in time with a specific wavelength. We will get that wave, that is, which has omega equal to 0, a geostrophic flow, and this is achieved. And the reason why we don't have a zero velocity is because we now say that the the Coriolis parameter is varying with latitude. So if it were not varying with latitude, we would have gotten a frozen geostrophic flow, geostrophic current, which we got in the earlier lecture. Okay, that would have been omega equal to 0.